So far you've been learning about discrete random variables that can take on values in discrete sets like finite sets, and the functions that model their random behavior, their probability mass functions, PMFs, and corresponding cumulative distribution functions, CDFs. This video is an introduction to continuous random variables. They still have functions that model their random behavior, but the name for the first one is different. Instead of a probability mass function, they have a probability density function, or PDF. They still have cumulative distribution functions, CDFs, just like discrete ones did. A continuous random variable, typically denoted by a capital letter like capital X, is a random quantity. It doesn't take on values in a discrete set, but instead over a continuum, which basically means an interval on the real line. It could be a finite bounded interval, or it could be the entire real line, according to some probability model. We initially model the probabilities with a PDF, a probability density function. This is a function little f of little x, which has positive outputs only over the possible sets of values of capital X. These output values, unlike the discrete case, are not probabilities. They're actually probabilities per unit length along the horizontal axis. They can be conceptualized not as masses, but instead mass densities. And again, this idea of a mass will make more sense when we talk about means later on. Thus the name, probability density function, PDF of capital X. The graph is often displayed as shown below. Technically, it is defined for all real numbers little x. Though it might be 0 over most of the real line, there are plenty of important examples, including the normal curves, which are defined and positive for all real x, however. So take a look at this example. You can see it's a linear function. We do want the total area under this graph to equal 1 because the areas are going to correspond to probabilities, and you could take the time to double check that the area under this graph is equal to 1. But again, how do we interpret the outputs? You can see there's a shaded trapezoid underneath the graph above the interval where x goes between 4 and 4.2. The area of that region would be the probability that x takes on values between 4 and 4.2. And you can think of that as an approximate form as a product. Little f of 4 times 0.2. The value of the density function at 4, the left endpoint of the interval, times the length of the interval. That's why this can be thought of as a probability per unit length. Moreover, since f of 4 is approximately 0.25, the product 0.25 times the length of the interval, 0.2, is approximately the probability, 0.05. Also note that the outputs of the PDF are larger when x is large than they are when x is small. Intuitively, this means that the probability that x is large will be larger than the probability that x is small. And you would also then expect that over many runs of the random experiment that this models, that the average or mean value of x would be larger than 2.5, which would be halfway between 0 and 5. We will continue thinking about this example in the slides to come. Just like the discrete case, probabilities for continuous random variables can also be described by cumulative distribution functions, or CDFs. The probability model for capital X can also be described by another function which accumulates or adds up the probabilities from the PDF. It is therefore called the cumulative distribution function, or CDF, of capital X. But remember, the values of the PDF, when you have a continuous random variable, are not really probabilities. They're probabilities per unit length, probability densities. So to add them up doesn't entail doing a literal addition. If you think about it, it would have to entail doing an integral, integrating the PDF to get the CDF, and that's what we'll see in coming slides. This function in abstract form can be written capital F of little x is the probability that capital X takes on values less than or equal to little x. Again, think of capital X as your abstract random variable and little x as being particular numbers. Note that by rules for probability, this would mean that the probability that capital X takes on a value between a and b inclusive would be the probability that x is less than or equal to b minus the probability that x is strictly less than a. However, that is the same as capital F of b minus capital F of a. Because that's strict inequality, that x is less than a, doesn't really matter. The probability that x is less than a will equal the probability that x is less than or equal to a, effectively because the area under the PDF Under 1 point is 0. Areas of lines are 0. The graph of the CDF is often displayed like the one shown below. Technically, again, this is defined for all real numbers little x. Note that this function is increasing just like in the discrete case, though not necessarily strictly so. Because our PDF takes on strictly positive values between 0 and 5, that is the interval along which capital F, the CDF, is strictly increasing. Here, the vertical distance, which is a difference, represents the probability. In the case where x is between 4 and 4.2, just like before, here you would see it's the value f of 4.2 minus f of 4. It's the vertical distance between those values, which again is about 0.05. Also note that the graph of capital F, when x is between 0 and 5, is concave up. This reflects the fact that the PDF, little f, is increasing. In fact, capital F is an antiderivative of little f. The derivative of capital F is little f. Let's be precise about the calculus relationships between the PDF and CDF of a continuous random variable. By definition, probabilities are computed from the PDF by definite integration, by finding the area under the curve. The probability that x is between a and b, and it doesn't matter whether it's inclusive or exclusive, it doesn't matter whether it's less than or equal to's or strict less thans, can be computed as the definite integral of the PDF as x goes from a to b. To be a valid model, we require that the integral over all x, from minus infinity to infinity, equal 1 in the abstract. Since capital F of x, the CDF, by definition, is the probability that capital X is less than or equal to little x, it follows that that can be represented as an integral as well. Capital F of little x is the integral of the PDF from minus infinity to little x. The variable for this function, capital F, is this upper limit of the integral. The u doesn't really mean anything, it's just a dummy variable. I can use any letter that I want other than x. When you look at this kind of equation, I hope it reminds you of the fundamental theorem of calculus. By the fundamental theorem of calculus, if you differentiate an integral like this, you will get the original integrand. In other words, capital F prime of little x equals little f of x for all x. Okay? Don't use a u on the right-hand side of that equation. We are treating x as the variable. Again, the u in the integral doesn't really mean anything. Of course, we already know that this probability that we had originally can be computed as capital F of b minus capital F of a. That also represents the fundamental theorem of calculus. In our last couple slides, we're going to take our abstract model from the first content slide and relate it to real life. We're going to make it concrete. We're going to suppose that capital X is the value in thousands of dollars of a certain model of car that is at least 10 years old, chosen at random from the population. I'm choosing old cars because their values are lower, so it's going to be more realistic that way. For simplicity, assume the possible values of capital X are between 0 and 5, and remember the units are thousands of dollars. We have to base our model on gathered data. Based on gathered data, the PDF for capital X could be this particular function, and if you go ahead and take the time to graph this particular function, you'll see its graph is the same as the graph that we saw on the first content slide, where x goes between 0 and 5, and the areas under the PDF give you probabilities. And it makes some intuitive sense if you think about the application here, that for cars in this model that are at least 10 years old, perhaps most of them would have values closer to $5,000 than closer to $0. It's maybe not the case, but it's certainly plausible. Certainly this function is non-negative. It's greater than or equal to 0 for all real x, and you should check that the integral over the real line equals 1. And here would be the calculation you would do. You do need the antiderivative of the PDF here, which would be 0.02 x squared plus 0.1 x, and evaluate that from 0 to 5, meaning plug in 5 and subtract what you get when you plug in 0. And you can check that you get 1. And that would also mean, for example, if we want to calculate the probability that x is between 4 and 4.2, we would do this integral from 4 to 4.2, which would mean to evaluate the antiderivative from 4 to 4.2, plug in 4.2, subtract what you get when you plug in 4, and you can take the time to check that that's 0.0528, approximately 5%, as we saw graphically on the first few content slides. Finally, let's compute the CDF for this example. The CDF, as we've seen, is a particular antiderivative of the PDF, and in fact we will see that it's the particular antiderivative that we already used to integrate the PDF, but we need to confirm that. In this example, if x is between 0 and 5, then we can represent the CDF, capital F, of little x as the definite integral of the PDF from 0 to x. Again, when you look at this, the variable is in the upper limit of the integral and the u doesn't really mean anything. If we evaluate this definite integral by using the antiderivative 0.02u squared plus 0.1u, as u goes from 0 to x, plug in x, subtract out what we get when we plug in 0, we get 0.02x squared plus 0.1x minus 0. And that is the same antiderivative, again, we used on the previous slide, and that is the CDF. Technically speaking, this is defined for all x. If x is less than 0, then capital F of x is equal to 0. And if x is bigger than 5, then capital F of x is equal to 1. Therefore, the final answer for the CDF as a piecewise function is this function that you see right here. And once again, we can use this to compute probabilities. Once again, the probability that x is between 4 and 4.2 is about 0.0528, here represented as a difference, capital F of 4.2 minus capital F of 4. And if you graph this function, you'll see the same graph that we saw in the second content slide.